Okay, so the next question, what causes more change in entropy, melting 1 kilogram of ice at 0 degrees Celsius or evaporating 1 kilogram of water at 100 degrees Celsius?
It's the same concept.
So, and we have all these different answers here.
But don't we already know that with water, that has a higher specific heat capacity? So would that factor in?
Well, it actually doesn't.
Okay.
The two situations are melting, they're the same mass, melting ice at 0 degrees Celsius and evaporating water at 100 degrees Celsius. So we're not changing temperature. We're doing constant temperature situations here. And what is the equation for change in entropy?
Delta S equals something.
Q over T.
Yes.
So we have to, well, what do we have to do here?
We have to find the Q.
Okay. So find Q melt and Q evaporate.
Oh, so then would we be doing Q equals M L V for the evaporation?
That's right.
And then M L F for melting? Okay.
Yep. So we have to look up the latent heats of vaporization and fusion for the water, and we have to divide by temperature. So delta S, actually, I guess they called them ice and water. I'm still going to stay with melt and freeze, or not melt and freeze, melt and evaporate. So delta S melt, I'm going to call it, is equal to Q melt over temperature melt equals mass times latent heat of fusion of water over the temperature melt. So my mass is 1.00 kilograms. Latent heat of fusion. What's the latent heat of fusion for water? We look it up, right?
Isn't it like 2 something?
I think it's 334
Oh, the 330, yeah.
kilojoules per kilogram.
It's for melting.
Pardon?
LF.
It's for fusion melting, yes.
Okay, the latent heat of fusion for water is 334 joules per gram. So that would be 334 kilojoules per kilogram. And what's the melting temperature of water?
0. No, 32.
It's 0, but we have to use kelvins because it's not a change in temperature. So that's over 273.15 kelvins.
Oh, can you see, please?
What happened to it?
Not that your family isn't awesome.
I'm glad you recognize that they're awesome. Okay, so we have to do this calculation. So 334,000 divided by 273.15. What's that number?
Wait, what? Oh.
Yeah, it's because it's kilojoules.
Um, 1.222.
Okay, so 1,223 joules per Kelvin. And then we do our next calculation, change in entropy for evaporation is equal to Q evaporation over temperature evaporation. It's equal to mass times latent heat of vaporization over temperature evaporation, which is 1.00 kilograms. And the latent heat of vaporization for water is 2230
That's right.
kilojoules per kilogram. And then what's the temperature for
100?
the evaporation. 100 degrees
but-
Celsius,
so
we have to use.
373.15.
And so once again, we put that in our calculators. I think we can all see which one's bigger here. So we have 5976. Now, you can see in the answers, they must have had a different, mine came from Encyclopedia Britannica, the latent heat. They had apparently a different value because their number is off by a small amount. We have 5.976 and they have 6.05. Okay, now we can answer very simply which number is bigger.
Evaporation.
Okay, so evaporation is bigger. So we're going to go with evaporation, one of these two, and then we have to look at the rest of it because the latent heat of vaporization is much greater than the latent heat of fusion. That's true. So this is true. And entropy changes are greater at higher temperatures. It depends on how much heat you have, if it's a bigger or smaller entropy change, right? It was about the latent heat of vaporization. So that means this had to be the right answer. Any questions?
Mm-hmm.
So let's see what our next one is. Oops. Stacks two. What is the change in entropy when 100? Okay, so this one's going to be a quickie.
We don't have that one.
Well, it's different for each person. That's if more than one person does them, if it's not just Nice that does them. I was telling Nice that there was at least one question on the test that she was the only one who had done it. Okay. What is the change in entropy when 100 joules are added by heat to water at room temperature? What's our equation for change in entropy?
Delta S is equal to Q over T.
All right.
So we're looking for delta S again.
So what is our Q?
What was the question again? Sorry.
Sorry, it hasn't shown up for you. What is the change in entropy when 100 joules are added by heat to water at room temperature?
So 100 joules.
Okay, so our heat is 100 joules.
That's our 10.
And what's the temperature?
So
that is, it says room temperature.
20 degrees Celsius.
Room temperature is 20 degrees Celsius.
That's 293.
Yep.
Okay.
Yes, you just do 100 divided by 293. 0.15 technically, yeah.
0.341122.
Notice the units of entropy are joules per Kelvin. The same as the units of Planck's constant. Right, so that was a quick one.
Mm-hmm.
We like quick ones.
Still not showing.
Yeah. The next one is exactly the same idea. It says if 30 joules are added by heat to water at 12 degrees Celsius, what's the change in entropy?
You get the Q.
There's no reason to do that again, right? It's just the same calculation. The next one, if Q is this and T is this, what's the change in entropy? Same thing again. That one has been answered by Mr. James Dickerson. Given a container with 4 identical molecules, how many microstates are there for the macrostate in which 2 particles are in the left half of the container and 2 are in the right. So let's look at that one. The reason for this question is primarily to make sure you understand what entropy is about. I see that is not coming up for us at all there. It says sinking. There we go. Given a container, okay. So how many microstates are there for the macrostate in which 2 particles in the left corner of the container and 2 are in the right half?
4. Right.
Okay, 2 particles in the left half and 2 are, oh. So it's just like that, right? 2 in the left half, 2 in the right half. So given the way it's specified, we're going to say, okay, vertical isn't going to matter at all. And where it is left to right doesn't matter if it's on the left side or the right side. So the options we have are change the colors. Let's make them each one a different color. Okay, so there's one microstate. What else could I do?
Switch.
Okay, I could switch, and I could switch the green. Well, actually, the positions of the green and the purple don't matter because it doesn't matter what the vertical is. It's just which side it's on. But I could switch
Green,
the,
pink, green.
yeah, actually, let me copy and paste. Be a little quicker probably. Copy. So I could just exchange those two. That's a new state, right? New microstate. Or I could exchange these two. There's a different microstate. And how many more do I have?
2 more.
2 more, right? so we can see, I don't have, do you see, Brittany, 2 more? Okay, then we'll go on. So I have done my exchanges for the top. Now I'll do exchanges for the bottom. So there I did another exchange. And finally, the last one will be exchange those two. So if you look here now, we have green and purple on the left, magenta and purple on the left, blue and purple on the left, green and magenta on the left, and green and light blue on the left. So that should be all of our different options. If I, oh no, there's one more. There's one more. I'm sometimes not perfect. In fact, I'm never perfect, but let's not. We could change both. Of course, forgot the changing both option. And so I should have just rotated it. Would have been the quickest. There. Now we have all the options. So how many microstates were there?
6.
6. And depending on your book, they might write it as W equals 6 or omega equals 6. I really don't like to put W equals 6 because that's work right now. So the number of microstates is 6 for that macrostate.
That's microstates.
Yeah, omega is the symbol for microstate. It's
Is
like I
that
said,
capital?
omega, or yeah, it's a capital omega. Yeah, I told you about the student who said, "Yeah, I used this." And after class, not wanting to embarrass me, she comes up and tells me that's not omega. I was in a sorority. I had to memorize them all. What? There's uppercase? Or, yeah. Anyway. First law of thermodynamics. I'm not going to copy and paste this because there's no work for it. Which principle does the first law of thermodynamics state? So just tell me the first law.
That the internal energy, which is delta U, equals the Q in minus the work out.
Okay, there was one thing that she said that was technically incorrect. Her idea was right there.
Energy is conserved.
Okay, energy is conserved. What she described was the equation for energy is conserved. So both of those are correct. The one technical thing she said is she said internal energy, which is delta U. Delta U is correct, but what is delta U? Change in internal energy. U is internal energy. The internal energy can change, but delta U is equal to. So the options they give us are the ideal gas law, the transitive property of equality,
What?
the law of conservation of energy, or the principle of thermal equilibrium. It's
That one.
conservation of energy.
Oh, what is the conservation of energy, not the thermal equilibrium one? Is that the same thing?
No, the thermal equilibrium one. Yeah, thermal equilibrium is when two things are in thermal equilibrium, no heat is passing between them, and that, according to the second law, requires them to be the same temperature.
Okay.
Okay, the next one is, again, one that requires no work. Can the value of thermal efficiency be greater than 1? No. Why not?
Because it's the probability of, like, you can't have greater than a 100% chance of being efficient. You can't even be 100% efficient.
Okay, efficient is transferring from A to B.
Yeah, because
And you can't transfer more into B than you took out of A, right? You can only transfer what you took out. You could always take out of A and drop a few before it gets to B, but you can't go the other way. So the thermal efficiency can never be greater than 1. And in fact, it can never even be 1, which was on the test. According to the first law of thermodynamics, energy output can never be more than the energy input. That would work since the first law is conservation of energy. No, according to the second law, energy output can never, no, not the second law. Yes, according to the first law, energy output can be more than, well, that's clearly wrong. Yeah. Okay, this is good. If more energy is transferred into the system by net heat as compared to net work done by the system, so more heat is added than work is done by the system, then what happens with the difference in energy?
The heat is, like, transferred out into the environment? Or, like...
Well, you have, I'm going to copy this just so we can make a picture.
Because if you put in more than what you're getting out, then something is getting lost to the end.
Okay, so we have more heat. Scroll down. Make it update, maybe. Where's my cursor? There it is. Okay, so we have more heat, or more heat going in than work coming out. So we have this system, and we have heat coming in, and we have work going out. If we have more energy coming in than going out, what has to change for the system? Okay, the temperature will change because delta U is equal to Q in minus work out, right? And so
internal energy will increase.
That's greater than 0. And so internal energy will increase is the correct answer. And that will manifest in an increase in temperature.
Yeah.
So you were thinking the right lines with the increase in temperature, but
There's the middle step.
but temperature isn't the energy, so that's why the difference in energy goes into increasing the internal energy.
Okay.
Not sure why that didn't work. What is the pressure volume work done when a piston in an engine cylinder with cross-sectional A moves up a distance D as energy is added? I'm going to, well, I of course hit the wrong button. This is going into, stuff that we've already looked at.
Mm-hmm.
So if you want to go on to new stuff, that's fine. Tell me what to do.
Mm.
Can we do more stuff with like the macro states and stuff, or do you guys want to do something else?
Do you want to shift to the homework that you were talking about?
Yeah.
Do you have strong feelings, Brittany? Yeah.
No, I'm doing it now. I'm just.
Oh, I can't go to the homework say. Yeah,
That's
no,
fine.
I can. I was going to say I can't go this way, but you won't see scores, so I can.
Jordan will be here soon, so I'll see if you
You can.
Uh-oh.
I can do the homework with Jordan.